This is lesson 26 in our Calculus 3 series, Triple Integrals. In lesson 24, we saw the computation of total mass of a thin plate, and with that, density was given as mass per unit area. Now we're interested in finding total mass of a solid, and in this case, density will be given as mass per unit volume. So the double integral we saw in lesson 24 is now going to be a triple integral. The density function for the solid is now a function of x, y, and z, and we're going to be integrating over that three-dimensional solid, that three-dimensional domain. So let's define now the triple integral. Here's our domain. To start out, we're using a rectangular box where x goes from a to b, y goes from c to d, and z goes from r to s. And at each one of these little sub-boxes, let's pull one out and take a look at it. We've got the dimensions delta yj, delta xi, and delta zk. And the point at which we will be evaluating the function is some point in this box. We'll call it xi star, yj star, zk star. And so the Riemann sums for our triple integral look like this. We've got summation over I, over j, and over k. We've got the function value here, and when we're computing total mass, that's going to be the density function, but in general, it's any function of x, y, and z multiplied by our volume element here. And of course, the triple integral is defined as the limit of these Riemann sums as the maximum delta xi, delta yj, and delta zk go to 0. Just like we had in double integrals, we have Fubini's theorem that says this triple integral is the same as the iterated integral. So now we know how to compute this triple integral. And note here what I have written. I have dx, dy, dz. Notice the bounds on x are a and b, the bounds on y, c and d, the bounds on z, r, and s, just like the image of the domain that we had. But keep in mind that the iterated integral can be computed in any order here. So we could have this dz, dy, dx, dz, dx, dy, dx, dz, dy. There's 6 options here, right, of how to order these 3 variables. And so we can compute in any order that's convenient for us as long as we have the appropriate bounds in that order. But of course, most of the regions that we're interested in are not rectangular boxes, so we should talk about how to integrate over a general region in R3. And similar to what we did with double integrals, with triple integrals we want to talk about 3 types. The type 1 region I like to call a top to bottom region, because the top of the solid and the bottom of the solid can be described by z as a function of x and y. So here we have z is equal to u2 of x and y, and z is equal to u1 of x and y. These are the top and bottom surfaces for this solid. Once we identify the top and bottom surfaces, what we want to look at is the shadow that's cast in the xy plane, and then describe that region as we would for a double integral. So our iterated integral looks like the integral of f of x, y, z. Here we're integrating on z first because we're recognizing z as a function of x and y for top and bottom of the solid. So we've got z going from u1 of xy to u2 of xy. And once we've taken care of z, we look at the shadow from this solid down in the xy plane, and we want to describe that region the same way we would for a double integral. So in this case, I'm kind of breaking it up here and saying y is written as a function of x for a top curve and a bottom curve here. Y is equal to h2 of x on top, y is equal to h1 of x on the bottom. And so y goes from h1 of x to h2 of x. And then x goes from a to b, whatever constants we have, a to b. But keep in mind that with this type 1 top to bottom region, we might also have the shadow region written instead as dx dy, and with x as a function of y, and then constant bounds on y. Now a type 2 region is what I like to call front to back, because we have x is a function of y and z for the front of the solid, and also x is a function of y and z for the back of the solid. And so once we recognize those surfaces, we can make that our inner integral. And we have our bounds on x here from u1 of yz to u2 of yz. And then we look at the shadow cast in the other variable plane. So we integrated on x already, now let's take a look at y and z. We take a look at the shadow in the yz plane and describe that region the same way we would for double integrals. So here, again, I'm showing it as z is a top function of y and z is a bottom function of y. And so those are the bounds on z. And then we have constant bounds on y. A type 3 region is a right to left region. We have y as a function of x and z for the right and left surfaces of our solid. And once we describe that variable and those bounds, we take a look at the shadow that is cast in the xz plane and describe that domain as we would for a double integral. So let's take a look at an example. Find the mass of the solid bounded by the coordinate planes and the plane x plus y plus z equals 12 with the density function rho of xyz equals 2 plus x. Now we saw this region in one of our previous lessons. We know that this is a plane and we know that it intersects each axis at 12. Now we can recognize this region as a top to bottom, as a front to back, even as a right to left. So let's set up this triple integral all 3 ways. Or actually, I should say all 6 ways. As a type 1 region, a top to bottom region, our top surface is going to be this plane, z equals 12 minus x minus y, and our bottom surface is going to be z equals 0, the xy plane. Once we found the bounds on z, we look at the shadow that is cast in the xy plane. That's this shadow here, this region here. We know that the equation of this line in the xy plane is y equals 12 minus x, or x equals 12 minus y. So we could describe this region in 2 ways. We could say y goes from 0 to 12 minus x, and with that, x goes from 0 to 12. Or we could say x goes from 0 to 12 minus y, and with that, y goes from 0 to 12. So again, here are the bounds on z, using the given plane and the xy plane as our top and bottom surfaces. So those are going to be our bounds on z, and z will be our inner variable on both of these integrals. But now we could then choose to integrate on y going from 0 to 12 minus x, and then x going from 0 to 12. Or we can have x going from 0 to 12 minus y, and then y going from 0 to 12. So far we have 2 iterated integrals that describe the mass that we're looking for. Let's take a look at describing this region as a type 2 front to back solid. Then the plane x plus y plus z equals 12 is going to be the front surface. So that's x equals 12 minus y minus z. And the back surface is going to be the yz plane, or x equals 0. So x goes from 0 to 12 minus y minus z. And then we'll look at the shadow that this casts in the yz plane. So let's take a look at the original picture again. This is our front surface, the pink that you see. And then what's the shadow cast from this in the yz plane? That's going to be just this triangular region here in the yz plane. That's here. And this line is either z equals 12 minus y or y equals 12 minus z. So again, we have 2 ways that we can describe this region. And so our triple integral can look like either of these. We can also consider our solid to be a type 3 region, right to left, where our given plane is the right side of our solid, and the plane y equals 0, or the xz plane, is the left side of the solid. And once we describe the bounds for y, that'll be our inner integral, and then we take a look at the shadow that's cast in the xz plane. So here's our right surface, and our left surface is the xz plane. And now the shadow in the xz plane is just this region here. So we've got the line z equals 12 minus x, or x equals 12 minus z, depending on how we want to describe that two-dimensional region. So we've got these two ways to describe that region. And so we've got these two triple integrals. So we've set up 6 different triple integrals to represent the same computation, the same mass computation that we're looking for. And so, of course, they'll all give the same answer, but let's go through the computation for one. So we'll take the last one that we wrote down. Here we're going to integrate on y first. So we multiply our 2 plus x by a y and plug in the bounds and subtract. And so we're here. And then integrate with respect to x. Now we need to plug in our bounds and subtract again. So we're here. And of course it takes a bit of simplifying because we still need to integrate again now with respect to z. So with these I multiplied it out, but with these I used a u sub. So integrating with respect to z gets us here. And then we plug in our bounds and subtract. Bit of simplification is necessary. And we get 1,440, and that's our total mass of the solid. Let's take a look at a problem that we've seen before. Find the volume of the solid between z equals 16 minus x squared minus y squared and z equals 3x squared plus 3y squared. Now in lesson 23, we recognize this as a top surface and a bottom surface, and we did some subtracting with double integrals. The domain that we were integrating over was the shadow here that we get in the xy plane, and that was x squared plus y squared less or equal to 4, and that determined our bounds here for y and then for x. But then we recognized that it would be easier to solve in polar coordinates, so we wrote the integral in polar coordinates. Now we could also use a triple integral to find the volume of this solid by integrating the function 1 and considering this our entire domain over which we're integrating. So we have z going from 3x squared plus 3y squared, that's the bottom surface, to 16 minus x squared minus y squared, that's the top surface. And then just as we did before, we take a look at the shadow in the xy plane and then describe that region as you would for a double integral. So it's the same bounds we had on that double integral for y and for x. Because notice when we do this integration, integral of 1 dz gives us a z. We plug in these bounds and subtract and we get exactly this integral here. And we continue from there. Similarly with polar coordinates, we have our top and bottom functions, but now instead of z equals 3x squared plus 3y squared, we have to write this in terms of r and theta, so that becomes z equals 3r squared. And this is 16 minus r squared. So those are our bounds on z. And then as we take care of the other two variables, we have r dr d theta, so we've got this copy of r that will move inside the integral. And the bounds on r and theta are exactly what they were before for the double integral in polar coordinates. And notice when we integrate on z, we're going to have a z here, we're going to plug in these bounds and subtract, and again we'll end up with exactly this integral to compute. Similar to what we saw for average value of a function of two variables, using a double integral, now we have the average value of a function of 3 variables over a domain using a triple integral. So the average value of w is equal to f of x, y, z over domain D is 1 over the volume of D times that triple integral. And remember that we can compute the volume of D by using a triple integral over D of just the function 1. That's what we were just doing in the last example. And as we did above, we had our computation for mass by integrating the density function over the domain D. And with that, we also have our computations for center of mass and for our moments of inertia. So for center of mass, we've got the natural extension from what we had in double integrals. We've got 1 over mass of the domain D multiplied by the triple integral of x times the density. For the y-coordinate of the center of mass, we're integrating y times the density function, and for the z-coordinate, z times the density function. And for moments of inertia around the x, y, and z axes, we have these integrals. So let's take a look at an example. Let's find the center of mass of the top half of the sphere of radius a. Now we're talking about the center of mass, and based on the symmetry of the top half of the sphere, we realize that the x-coordinate and the y-coordinate should both be equal to 0. So really the question here is, what's the z-coordinate for the center of mass? Since they didn't give us a density function, we can assume that the density is 1, and so the mass, the total mass, is equal to the volume of the hemisphere, and so that's 1/2 the volume of a sphere of radius a, and so that's 2/3 pi a cubed. So we're going to divide by that and take the triple integral of z multiplied by our density function, which is 1. So now as we're creating this triple integral, we could integrate the variables in any order we want. I look at this as a top surface and a bottom surface, so I want to start with integrating on z. And after that, I recognize that our domain in the xy plane is going to be a circular disk. And that's easiest in polar coordinates. So describing the top surface z, this is x squared plus y squared plus z squared is equal to a squared. So solving for z squared and then using x squared plus y squared equals r squared gives us z equals radical a squared minus r squared. And then for the circular disk of radius a, we have r going from 0 to a and theta going from 0 to 2 pi. So integrating on z, we're here. I brought this constant r into the integral. So we have r z squared over 2, plugging in our bounds and subtracting, we're here. So I multiply through the r and integrate with respect to r. Plug in our bounds and subtract. And notice this is all constant here, right? We've got a constant multiple in front. This is all constant because theta is the variable that we're left with. So combining the 3 over 2 pi a cubed and the 1/8 a to the 4th, we get 3a over 16 pi. Integrating d theta, we get theta. Plugging in our bounds and subtracting, we get 3/8 a. And that's the z-coordinate of the center of mass for that hemisphere. Now let's take a look at an example where we want to sketch the solid whose volume is given. So here's the volume of the solid. What's the solid look like? Here we see that y goes from x squared plus z squared to 4. So y is going from x squared plus z squared to 4. Then x is going from 0 to radical 4 minus z squared, and z is going from 0 to 2. So how can we sketch this solid? Let's start by setting up our axes. Now y equals x squared plus z squared. That's going to be a sideways facing paraboloid, but let's take a look at the traces if we need to. Y equals x squared plus z squared. If x equals 0, we get y equals z squared. So this is a parabola in the yz plane. Right, this is y, this is z. And if we take z equals 0, that gives us y equals x squared, another parabola now in the xy plane. So this is now coming forward and back. So this is coming forward, and that's, say, going back. And if we have y is equal to a constant, then we get x squared plus z squared is equal to a constant. And that's going to give us a circle. We might as well recognize this trace as y equals 4 because that's the other bound on y. So the left part of our surface is this paraboloid, and the right part of our surface is the plane y equals 4. Now let's just make sure that the bounds we have for x and z also go along with the solid that we've just drawn. X goes from 0 to radical 4 minus z squared. Well, we know once we take care of the inside variable, we're supposed to take a look at the shadow that we would get in the xz plane. In this case, we took care of y. Let's take a look at the shadow we get in the xz plane. That shadow is going to be this circle. And this is the circle x squared plus z squared is equal to 4. And so yes, if we solve for x, we get x equals radical 4 minus z squared. But notice the lower bound on x is 0. That's telling us we don't have any of this paraboloid, any of this region that is behind the yz plane. So by looking at the bounds here, we realize we need to get rid of that back part. And then what that does to our paraboloid is that it gives us only the front half. So we could erase this part as well. And now let's take a look at our bounds on z. We also have that z is bounded below by 0. Z is going from 0 to 2. But in the region we have here, it looks like z is going from negative 2 to 2. So we have to make another adjustment. We don't want any of these negative z values. That tells us we don't want the bottom part of this paraboloid either. And this is a solid whose volume is given. Again, we have y going from x squared plus z squared, that's that paraboloid, to 4, to the plane y equals 4. And x goes from 0 to radical 4 minus z squared. X goes from 0 to radical 4 minus z squared, this part of the circle here. And z goes from 0 to 2. So this is the solid that we're talking about. Now, it would be a good exercise for us to go and write another triple integral that would represent the same volume. So let's write a triple integral that doesn't have a y as an inner variable, but has a different inner variable. So how can we do that? Let's notice here that the integral we were given is a right to left integral. We have a right surface y equals 4 and a left surface y equals x squared plus z squared. Now instead of describing this as a right to left region, let's describe it as a front to back region. That would also be a natural way to describe this solid. So our front surface would be the same paraboloid, y equals x squared plus z squared. So x is going to be equal to radical y minus z squared. And notice that I chose the positive radical because we're only talking about x values that are positive. So x is equal to radical y minus z squared. And the back surface would be x equals 0, right? That's this yz plane that is the back surface here. So now we have a front surface and a back surface. And once we take care of the variable x, which we have here, we need to take a look at the shadow cast in the plane of the other two variables. So now we're just looking at what we have in the yz plane. So let me sketch that here. And this curve here is where x is equal to 0, right? So this is y equals z squared. And this is y is equal to 4. So we have y going from z squared to 4. And then with that, what are the bounds on z? We have z going from 0 to 2. So we have z going from 0 to 2. We have y going from z squared to 4. And we have x going from 0 to radical y minus z squared. And with these bounds, now we can set up another triple integral. So our inside variable is going to be x. We have 0 and radical y minus z squared. And then we're going to integrate on y. We have z squared to 4. And then on z going from 0 to 2. That's another integral that represents the same volume. As you can see, it's important with this lesson to be able to sketch the quadric surfaces and some basic planes so that we can understand the solids over which we're taking volumes or for which we're finding the mass, because many of these exercises do require sketching. And this concludes our lesson on triple integrals.